Good day. Now that we have learned the dangers of dust explosions, we need to understand the science behind them. We will start with the fundamentals of combustion. We begin with the foundational model called the fire triangle. This heuristic establishes the three stoichiometric and energetic prerequisites for typical combustion: the fuel, the oxidizer, which is usually atmospheric oxygen, and the ignition source to supply the activation energy. For sustained combustion, however, we must use the fire tetrahedron. The fourth component added here is the uninhibited chemical chain reaction. This element represents the continuous production of highly reactive intermediates, specifically free radicals, which sustain the self-propagating exothermic nature of fire. Effective suppression, therefore, can target any of these four components. When dealing with dust hazards, a new model is required: the dust explosion pentagon. This model integrates the fire triangle with two critical physical parameters that differentiate a rapid combustion event from an explosion. The first is dispersion, which says that solid fuel must be suspended in the oxidant, which is air, at a specific concentration to form a uniform flammable cloud. This dramatically increases the reactive surface area. Second is confinement, which says that the reaction must be constrained within an enclosure. This confinement is what allows the rapid thermal expansion to translate into a dangerous, destructive pressure wave. Chemically, combustion is defined as an exothermic oxidation process. The general equation for an organic fuel is presented here. The key output is heat, which regenerates the ignition source and sustains the chain reaction. It is important to recognize that this is the equation for complete combustion only. In environments with insufficient oxygen, which is a common scenario in large vessels or dusty systems, incomplete combustion will occur. This results in the formation of hazardous byproducts like carbon monoxide, increasing fire risks and personal safety risk. The reaction of combustion is bounded by concentration limits. For dusts, we characterize this range using the minimum explosible concentration, or the MEC. The MEC represents the lowest concentration of airborne dust capable of propagating a flame front. If the concentration is well below the MEC, the mixture is too lean to support combustion, while an upper explosible limit, or UEL, exists for gases. A similar definitive limit is rarely observed for dusts. Instead, a highly concentrated dust cloud simply becomes too rich, where excess dust acts as a thermal sink, absorbing heat and inhibiting the necessary temperature rise. The regulatory goal is to ensure continuous operation at a concentration well below the established MEC for the material being handled. Finally, we need to understand the four main types of ignition sources, which provide the initial heat to start the reaction. Thermal ignition sources involve any hot surface, with the relevant parameter being the minimum ignition temperature. The surface temperature of any equipment must be maintained below the MIT to prevent ignition through direct contact or convection. Thermal sources include hot surfaces, which can arise from equipment malfunction, sparks, and open flames. Electrical ignition sources can come from short circuits, faulty wiring, or arcing in electrical contacts. Another major concern is the electrostatic sources. When fine dust moves through machinery, it builds up static electricity. This energy is measured by the minimum ignition energy, or MIE. Many industrial dusts can be set off by MIEs as low as 15 millijoules, which is less than the static shock you feel when walking across carpet. This makes grounding and bonding equipment absolutely essential to avoid explosions. Lastly, the primary source of chemical ignition is spontaneous combustion. occurring when certain dusts slowly react with oxygen at low temperatures, causing the material to heat itself up until it ignites. That will be the end for fundamentals of combustion.